Bismillahirrahmanirrahim. Hello students, welcome to the Electrical Engineering YouTube channel. In this lecture, I am going to demonstrate the DQ model of an induction motor and its implementation in MATLAB. DQ stands for direct axis and quadrature axis, and in this DQ model, the phase domain quantities which are uh, phase A, phase B, and phase C, for example, VA, VB, VC, the three phase quantities are converted to the modal domain. The modal domain is the direct axis and the quadrature axis mode, and these are the two phase quantities. So we will convert the phase domain quantities to uh, two phase modal domain quantities, and these two phase modal domain quantities have further two types, the stationary axis and the rotating axis. And first of all, the phase domain quantities will be converted to the two phase stationary frame or stationary frame quantities, and this transformation is called Clark transformation. And then the two phase stationary frame quantities will be transformed to the two phase rotating frame quantities, and this transformation is called Park transformation. The contents of this presentation are the transformation of voltage from phase domain to the stationary frame, and then the transformation of voltage from stationary frame to the rotating frame, and then flux computation, the calculation of current, torque, and speed, and finally I will discuss the results and discussion. So phase domain quantities can be transformed to the two phase DQ axis quantities by following these trigonometric identities. And in this figure, I have arbitrarily chosen the direction of VA over here. This is VB and VC, and it is always 120-degree angle between each of the three phases. And this is the quadrature axis, and this is the direct axis. So first transformation corresponds to the stationary frame, and that's why this is VQSS, and here Q corresponds to the quadrature. This S corresponds to the stator side of the induction motor, and this superscript S corresponds to the stationary frame. Similarly, this is the direct axis voltage referred to the stator side in the stationary reference frame. So first of all, we will translate the two axis quantities to the three phase quantities, and VA can be written, this is VA, it can be written in the form of VQSS and VDSS. So the angle between VA and VQSS is theta, so VA will be equal to VQSS cos theta. Similarly, this VA will be equal to the addition of this VDSS cos 90 minus theta. So this total angle is 90 degrees, this angle is theta. So this angle will be 90 minus theta. So cos 90 minus theta is equal to sin theta. So VA will be equal to VQSS cos theta plus VDSS sin theta. Similarly, we can write VB in terms of VQSS and VDSS, and this is VB, and VB will be equal to VQSS cosine of angle between VB and VQSS following the anti-clockwise direction. So the angle from this vector to this VQSS can be calculated by adding 120 degree. This is further 120 degree, and this is theta. So it will become VB equal to VQSS cos theta plus 240. Similarly, VB will be equal to VDSS. Now this whole angle is theta plus 240, and if we subtract 90 from this angle, we will reach this VDSS. So it will become VDSS cos theta plus 240 minus 90 degrees, and it will become sine 2 theta plus 240. So this is VB, and as I have told you, this is VB. And since we know that the period of cosine and sine functions is 360 degrees, so we can subtract 360 from this angle, and we will get the same result. And if by subtracting 360 from this angle, we will get theta minus 120, and here sine theta minus 120. And if we open these trigonometric identities, cos theta minus 120 by cos alpha minus beta, we will get this expression, and by opening sine theta minus 120, we will get this expression sine alpha minus beta. Similarly, this is VC and it can also be written in terms of VQSS and VDSS, and it will be equal to VQSS cos 120 plus theta plus VDSS sine 120 plus theta. So this is VC and it can also be expanded by using cos alpha plus beta and sine alpha plus beta identities. Now this model can be represented in terms of a matrix, and here we have VA, VB, VC. Here we have two phase quantities VQSS and VDSS in the stationary reference frame, and this is the third mode. These are the two modes, and this is the third mode. And third mode is called the ground mode, and ground mode corresponds to the origin of this axis, quadrature, and the direct axis. So we have to write zero over here so that we can represent these terms in the matrix form. So in the matrix form, this will become as I have written over here. And now we can do the inverse transformation by representing these VQSS and VDSS in terms of VA, VB, and VC. So same ideology will be applied over there, and you can do it by yourself, and you can transform the phase quantities to the modal quantities. And for simplicity, we should consider theta equal to 0. If we use theta equal to 0, all these expressions will become even simpler. And in that case, VA will be lying over VQSS, and these vectors will also be angularly displaced in the anti-clockwise direction slightly. So this will be the new orientation of all the vectors, and VA will be equal to VQSS, and this is VB, and this is VC. And in this equation, if I substitute theta equal to 0, VA will be equal to VQSS. Similarly, these expressions will also become simpler, VB and VC, and this matrix will also become simpler, and these are the new formulations if we assume theta equal to 0. And as I have told you, inverse transformation can also be done in the same way to calculate VQSS and VDSS in terms of VA, VB, and VC. And in that case, we will get such a matrix, and by assuming theta equal to 0, we will get this simpler matrix. Now, these stationary frame quantities can be transformed to the rotating frame quantities, and this transformation is called Park transformation. And here you can see this is the reference axis in the stationary reference frame, and this is VQS and VDS. So you have noticed that I have removed the superscript S from VQS and VDS, and this corresponds to the direct axis and quadrature axis voltages in the rotating reference frame. And this axis is actually rotating in the anti-clockwise direction, and the speed of rotation of this axis is equal to the synchronous speed of the induction motor. And synchronous speed of the induction motor is actually defined as the speed of the revolving magnetic field in the stator. And the similarly, the speed of this reference axis is equal to that synchronous speed, and this synchronous speed is actually equal to omega e, and the angle between the stationary frame and the rotating frame quantities is equal to theta e. So this is the angle, and the speed of rotation or the frequency of rotation is omega e. Now we can do the same transformation by using trigonometric identities to calculate VQS in terms of VQSS and VDSS, and vice versa. So this is VQS and this is VDS. They can be represented in the matrix form. Similarly, VQSS and VDSS can also be written in terms of VQS and VDS, and these are the transformations, and this is the transformation matrix. Now, important thing is that if we assume omega e equal to 0, or the speed of rotation of this VQS and VDS equal to 0, then theta e will also be equal to 0, and in that case VQS will be lying on top of VQSS and VDS will be lying on top of VDSS, and they will be equal. So you can also check it by putting theta equal to 0 in this expression. So VQS will be equal to VQSS, and VDS will be equal to VDSS. Similarly, you can do the same for this set of equations. VQSS will be equal to VQS and VDSS will be equal to VDS. So this idea will also be used when we build these DQ model of the induction motor in the coming slides. So the DQ model of the induction motor is actually started from transforming the phase domain voltages to the modal domain in the stationary frame, and then the transformation of stationary frame quantities to the rotating frame quantities. And after that, we will calculate the stator currents for the two axes, and those currents will be transformed from the rotating frame to the stationary frame, and then these stationary frame currents will be transformed to the three phase currents, and these three phase currents will be calculated as a result of this DQ model, which I will show you in the coming slides. And also these currents and these voltages will be used to calculate the fluxes inside the induction motor, and the calculation of these fluxes will also require the information about omega E and omega R. Omega E is the synchronous speed of the stator, and the omega R is the rotor mechanical speed. So these fluxes and currents will be used to calculate the electromagnetic torque TE of the induction motor, and combined with the applied load torque, we will calculate the omega R, which is the rotor mechanical speed, and that omega R will be fed back to these blocks, and these blocks will give us the currents and the fluxes. So this is the block diagram framework of the DQ model of induction motor, and here important thing is that we know the synchronous speed of the stator. The synchronous speed is equal to 2f over p revolutions per second, and omega e is equal to 2 pi n. And if we put ns over here, we will get omega e equal to 4 pi f over p, and theta will be calculated by integrating this synchronous speed, and we will get theta e. So this same principle is applied over here. We know the omega e because we know the operating frequency, we know the poles of the induction motor. So omega e is constant, and by integrating omega e we will get theta e, and that theta e will be used in the model. So this integration is done in this way. Here you can see this is omega e, which is a known quantity, and this is integrated, and the integrator we will use in this model is having an external reset to zero input. So the idea behind using this integrator is that when the output of the integrator reaches 2 pi, we will have to reset the integrator to 0. So you know that when the angle is increasing from 0, so when it reaches 2 pi corresponds to 0 degrees. So we can reset the output of the integrator from 2 pi to 0, and then it will start increasing again from 0 to 2 pi, then it will come to 0. So we will get such sort of pulses, and this is 2 pi. So when this output reaches 2 pi, the output of this subtractor block will be equal to 0. So initially when the output of this integrator is less, the output of this subtractor will be high, and as long as the angle is increasing, this output will be reducing, and when it reaches 0, the output of the subtractor reaches 0, it will reset the integrator, and when it will become 0, when the output of the integrator becomes 2 pi, so the difference will become 0 and it will be reset to 0. And we have used the falling edge property of this integrator. So when it crosses the 0 axis, the output of the integrator will be equal to 0. So by using this scope, we can see the output. So we will get such a sort of waveform. Now we will use the flux calculation model, and this flux calculation model is given in this textbook, and this textbook is modern power electronics and DC drives, and this is the second chapter of this textbook. And the DQ model of the induction motor in stationary reference frame and synchronously rotating reference frame is given in detail in this textbook. You can read this textbook, this content by yourself. This book is readily available on the internet, and the whole model is explained in detail. So I have used the same set of equations which are given in this chapter, and I have just implemented this differential equation model into Simulink, and when I run this model, I get the desired results. So you can see this is the equation for VQSS, VQS, this is the stator resistance. Omega B is the base frequency. And this is the d by dt of flux. FQS is the quadrature axis flux at the stator. And FDS is the stator, the direct axis flux at the stator. Omega E is the synchronous speed and omega E is the base frequency. So this is the first equation, and the same equation I have used over here. Similarly, you can also check the other equations. This is VDS, this is VQR, and this is VDR. Since I have used the squirrel cage type induction motor, so the rotor bars in squirrel cage type induction motor are short circuited with each other, making a closed loop. So when there is a closed path, the net induced EMF at the rotor side will be equal to zero. If we use a slip ring type or wound type induction motor, these terms will be equal to non-zero and we will have VQR and VDR over here. But in spiral cage type induction motor, these rotor bars are short circuited, so these voltages corresponding to the rotor side will be equal to zero. And from these equations, we will do some rearrangement and we will solve these equations for the derivative terms of the fluxes. So by doing the rearrangement, we will get these set of four equations. And similarly, these are the equations for calculating the mutual fluxes at the quadrature axis and the direct axis. Similarly, when we have calculated the fluxes, we will calculate the currents at the stator and the rotor sides. And by using these flux and the current values, we will calculate the electromagnetic generated torque by the induction motor. And by using this expression, we will calculate the omega r, and that omega r will be fed back uh, in calculating these fluxes. So here you can see this omega r is being used. So that omega r is actually calculated and then it is given back to calculate these fluxes, which you have also observed over here. So this is omega r and it is fed back to calculate these fluxes. So this is the data which I have used in simulating the induction motor, and this is the rotor resistance which is assumed as 1.15. Similarly, stator resistance, the self-resistance, self-inductance of the stator, self-inductance of the rotor, mutual inductance between the stator and the rotor, frequency, number of poles, moment of inertia, and a rotor inductance. This is the rotor torque, and this is synchronous speed. This is the base frequency. These are the reactances, which will be calculated by multiplying omega with the inductances. So first of all, that file has to be run, and this is the overall model of the induction motor. And here you can see the three-phase voltages which are applied over here. This is the DQ model of the induction motor, and it will give us the current which has been drawn by the induction motor, the electromagnetic generated torque by the induction motor, and the rotor mechanical speed. This is omega E, which is a known quantity, and this is the applied load torque. Initially, the load is kept to zero, but after 4 seconds of simulations, the load is suddenly applied as a 40 Newton meter, and then we will check the response of these currents. So now I will show you the Simulink file of the induction motor, and here you can see these are the phase voltages. I will show you all the blocks so that you can simulate this model by yourself. So this is the phase A. Similarly, this is phase B. It has a minus 120 degree of phase shift. Similarly, this is phase C, and here you can see minus 240 degree phase shift is applied, but the amplitude is same. Now we are considering initially the stationary reference frame. So omega E is kept as zero, and when we keep omega E equal to zero, the stationary frame quantities are equal to the rotating frame quantities, which I have shown you in the presentation. So this is the load torque, which is kept as 40 Newton meter, but it will be applied after 4 seconds of the simulation. So this is the model of the induction motor. These are the input ports, and these values are actually given to ABC to DQ0 conversion block, and this block can be achieved by simply using this gain block. This is a mux block, and these all of these blocks are available in this Simulink library. Okay, so this is a mux block. You can drag it to the Simulink model, and you can choose the number of inputs. And this is a matrix gain, and these values are written over here in this matrix gain, and these values are calculated. These values are actually taken from this matrix. Okay, so you can see we are transforming the phase quantities to the model quantities. So the values of this matrix can be calculated from here, and they have to be inserted in this block. So this value is, this entry is 2 by 3, this entry is minus 1 by 3. So you have to multiply 2 by 3 with each entry. Similarly, this will also be minus 1 by 3. This is 0, and this is minus 1 over square root 3. This is all 1 over square root 3, and this is 1 by 3, this is 1 by 3, and this is 1 by 3. So these values are considered in this model, and this is a demux block, and it will give us DQ and 0 modes. And these VQ, VD, VQ, VD, they will be used in this block. And here we will have to calculate FQS, FDS, FQR, and FDR. And these values are actually calculated using these expressions. So first we will calculate FQS, and FQS, for calculating FQS we have made a further subsystem, and here you can see this is VQS, this is omega E, this is FDS, and this is FMQ, and this is 1 over WB. This is a gain block, and by opening this presentation you can double check all the values over here. So this is VQS, which you can see over here, and this is minus omega E over omega B FDS. So this is omega E over omega B multiplied by FDS. This is FDS, and it will be subtracted from this quantity. And here we will have another subtraction which is available over here. So minus RS over XLS. This is RS over XLS, and this is FQM. Okay, FQS minus FQM. So this is FQS, right? This is FQS. This is minus FQM, and it will be given over here. And the whole term will be multiplied with omega B. So the whole term is applied with omega B, and then this term is integrated, and the output of the integrator will be FQS. So this FQS will be fed back over here, and the same procedure is applied for calculating this FDS, and this is FQR. Similarly, this is FDR, and these fluxes are calculated, and they are fed to these two blocks. So this block is actually calculating FQM, IQR, and IQS. So this is the calculation of FQM, and it will need FQS and FQR. When I open this block, I will get this subsystem, and here you can see this is FQM, and it is equal to XML divided by XLS. So this term is actually FQS divided by XLS, and this term is equal to FQR divided by XLR, and they are added together and they are multiplied with XML. So XML is written as XM star in this simulation, and it will give us FQM. So similarly, this is FQM, and then we will calculate IQS and IQR. So this is IQS, and you can see this IQS. over here FQS minus FQM over XLS. FQS minus FQM divided by XLS. Similarly, IQR, IDS, and IDR will also be calculated in the same way. So this is IQS, this is IQR, and again this block will be used to calculate IDS, IDR, and FDM. So this is FDM, this is IDS, this is IDR. Again, the same model is used to calculate these currents. And after calculating these currents and the fluxes, we will calculate the electromagnetic generated torque. So this torque is calculated in this block, and here you can see we have IQS into FDS minus IDS into FQS. Okay, it will be divided with omega B. This is 1 over omega B multiplied with P by 2 and then multiplied with 3 by 2, and it will be giving us the electromagnetic torque. And that electromagnetic torque is used in this block. This is the load torque, and they will be used to calculate omega R. So this is TE minus TL. This is 1 over J. So all these terms will be shifted to the left to solve for d omega R over dt. And after integrating d omega R over dt, we will get omega R. And that omega R will be actually used in all of these blocks, right? So this is omega R is used in these blocks. And this is the whole model of the induction motor. And here you have IQS and IDS, and these IQS and IDS will be first transformed to the phase currents. Okay, so this is the zero mode, and quadrature axis and the direct axis currents refer to the stator side are also injected in this block, and this is VAN. This VAN is actually used to calculate the its phase, which is omega t, and for this calculation of omega t, we have used a PLL block. This PLL block is also available in this Simulink library, and this is VAN, this is the frequency, and this is omega t. That omega t will be used over here, and it will transform these EQ0 modes to the ABC modes, and it will give us the three phase currents, and these three phase currents will be displayed over here. So this is a short way of calculating phase current from the model currents, but we can also use the inverse transformation which we have studied in this presentation. So we can transform the we can calculate the phase quantities from the modal quantities using this transformation matrix. So in first simulation, I have used this direct or shorthand model. So I will also show you another simulation in which I have used this transformation model, this matrix model. So now I will run this simulation, and I will see what results we get from here. So first of all, we have to run this file. So this file contains all the data to be used in the simulation. So let's run this file and click on add to path. And this is the simulation model. And in this simulation, I will also show you what are the settings of the solver which I have used. So click over here, and here you can see this is the simulation type. This is the solver here. Maximum step size is chosen as auto, and the relative tolerance is chosen as 10 raised to power minus 3. So I think all data has been seen. Now let's run this simulation. So I will click on run. So this is the simulation which is running. So now let's check the three phase currents. Let's click on auto scale. So here you can see this is the motor current, the which is which the motor is actually drawing from the source. And before the simulation of 4 seconds, the load torque was kept as 0 and the motor was only taking 20 amperes. And at 4 seconds, we have applied a load of 40 Newton meter. So you can see the motor is drawing more current because the load has been applied. And you can also magnify the plot. And here you can see these are the three phase currents. So this is a nice waveform. Similarly, we can also check the electromagnetic generated torque. So before 4 seconds, no load was applied, so zero torque was being generated by the motor. But after 4 seconds, a torque of 40 Newton meter has been generated by the motor to satisfy the load. Similarly, we can also check the rotor mechanical speed of the motor. And here you can see before 4 seconds, the motor was running at higher speed up to 320. But when we apply load at 4 seconds, the speed of the motor has slightly reduced. So it has come below 300 RPS, revolutions, radians per second. So this is the first case in which we have used the stationary reference frame because omega E is kept as 0. Now I will show you this second simulation, and in this simulation we are actually dealing with the quantities in rotating reference frame, and here you can see I have used omega E, and that omega E is calculated in this file. So this is omega E and it will be transferred to this constant block. So this is a constant block, and when you use the scope in the simulation, always go to settings, and these are the setting parameter values. In the history, you have to uncheck this option, and in the style, you can choose white, white, and black, black. And here you can use line width of your choice. So if we use higher value of line width, the plot will be uh, more visible. So again, we are transforming the phase quantities, the modal quantities in the stationary frame. So here I have used this topology as opposed to the other one in which a matrix was used. So here we can use this technique to calculate VQSS and VDSS first. Okay, and here you can also see the values minus 1 over square root 3. This is 1 over square root 3, and all other values can also be seen. And these quantities then transformed to VQS and VDS. So these are the voltage quantities in the rotating reference frame, and these are the trigonometric functions. These functions or these blocks are also available in the Simulink library, and you can. So this transformation is same which as I have shown you in this presentation. So this is VQS equal to VQSS cos theta e minus VDSS sin theta e, and the same thing has been implemented over here, and you can also check it by yourself. So this is theta e, and now this theta e is actually coming from this integration. As I have told you, this is omega e, this is the integrator block, and this integrator block has external reset as falling, and other settings can also be seen over here. And this is constant block of 2 pi, and this value is fed back to the subtractor block, and this output is given to this theta e, and you can also check this theta e from this scope. And we, after calculating VQS and VDS, same thing which we have done for the stationary case will be repeated over here, and these are the four blocks to calculate the fluxes, and these are the two blocks to calculate the mutual fluxes and the stator and the rotor currents. These currents will be fed to this torque generation block, and this is the same model as I have shown you before, and this is the torque TE, and that TE will actually, so that TE you can see this is actually fed back to this block, and this block will calculate omega R. Okay, and that omega R will be fed to this log. Okay, this is omega r. So this is the whole model, and here again I have used the straightforward way of transforming the currents from model domain to the phase domain by using this direct block. So this block is also given in the Simulink library. You can also use either this block or you can use the model which I have shown you in the presentation, and now I will show you that model. So this simulation I have prepared by using that matrix model for calculating these phase currents from the model currents. So these are the model currents, and they are converted back from the rotating frame to the stationary frame by using this transformation. So VQS cos theta e plus VTS sin theta e. So this model will give us, so this same model can also be used for the currents. These expressions are given for voltages, and these same equations can be used for current. So IQSS will be equal to IQS cos theta e plus ITS sin theta e, and similarly for this. And that model is used actually to first transform these IQS and IDS to IQSS and IDSS. Here we have IQSS and IDSS, and then we have used these values to transform these stationary frame currents to the phase currents. So for this we have used this model, right? Okay, so this model has been used to calculate VQSS and VDSS, and this model. This model has been used to calculate IA, IB, IC from IQSS and IDSS, and these values, this model has actually been built over here, and these additions and subtractions are used. These additions are subtractions are subsequently used in this block diagram to calculate IA, IB, and IC. So now I will run this model, and then I will check what results I get from this model. So same results are expected to achieve by running this model as well. So this is a rotating reference frame, and when I open this probe, you can see the same results are achieved over here. These are the three phase currents, right? Similarly, this is the electromagnetic torque which is generated by the motor, and this is omega r. You can also see the same behavior of the speed. Okay, so this model is also built using the rotating reference frame quantities, but in calculating the phase currents, I have used this PLL block from the Simulink library. So that simulation is also expected to generate the same results, which we can also double check by running this file. And this is our phase current. This is our electromagnetic torque. Okay, the same torque is achieved. This is the rotor mechanical speed. This is also same. So that is all about our today's discussion on DQ model of induction motor, and I hope you have enjoyed the lecture, and I hope you have learned the complex how to build the complex model of any mathematical expressions which are composed of differential equations in Simulink. So for watching more similar videos, please stay tuned to this YouTube channel. Until the next lecture, it's goodbye.